function, but deterministic, and you can achieve this in a randomized setting, like a randomized algorithm, but for deterministic, we're still like 8, 7, 8 in the base, and this base comes because to make it deterministic, you apply some algebraic tricks and techniques, and you end up doing something like Gaussian elimination or matrix multiplication, and this omega comes, and this basically 3 to the power, some 2 to the power blah omega, and that's the running time. So you get this extra omega for each of these algorithms because you have to do some rank computation in between for doing this dynamic programming. Okay, so that much about dynamic programming. And then let me go back to my talk. So I have taught you treewidth, okay? Okay, so here's my talk. Okay, I spent my 5-6 minutes telling you the things which you will not be able to understand in my talk. This is the place to go and look for. Okay, I will try to define those objects in my talk, but if you do not find it in this talk, here's a place to look for if you're interested. Okay, so what I'm going to talk about is what I call a subexponential time parameterized algorithm for k-path from planar graphs to directed planar graphs. Now, what Saurabh spoke about was k-path on general graphs and how lots of new techniques got developed under the way by just trying to design faster and faster algorithm for this problem. Now, for example, for k-path, we have an algorithm using narrow sieves which runs in time 1.66 to the power k. But if I give you a pattern like tree on k vertices and I say, hey, can you find this k pattern tree in your graph as a subgraph? So this is like a subgraph, tree subgraph isomorphism where the pattern is tree and host is an arbitrary graph. You can do this in 2 to the power k time using this algebraic tricks and techniques, and people were just looking to, oh, whatever this idea we have developed for k-path 1.66, can we push this for finding tree subgraph isomorphism? And short answer to the long question is that no, you cannot do this unless you find some very fast algorithm for SAT. So these kind of techniques are really just geared towards k-path in some sense. People didn't know that these techniques are geared towards k-path, but the most modern techniques about k-path can only work for k-path, and if you are just asked for tree, it doesn't. Because k-path has an amazing symmetry which you can exploit to discard many solutions. But tree, even though it has some symmetry, those symmetries are not useful in designing these kind of algorithms. Okay. So, but now what do I want to convey in this talk? So all those were like 2 power k kind of algorithm, 1.66 to the power k algorithm. In this talk, my algorithms will have a completely different form of running time. So what I mean by a completely different form of running time? So the main message which I want to give from this talk is NP-hard problems become easier when you have some restrictions on the input. Now in the old days, in the classical setting, people studied problems on quadral graphs, interval graphs, and they could show that many NP-hard problems became polynomial time solvable on these graph classes, right? And people had this amazing idea to find bigger and bigger graph classes where these basic NP-hard problems can still be solved in polynomial time. But the other way of restrictions is like you put some topological restrictions like planar graph, index minor free graph, edge minor free graph, or graphs which can be defined as an intersection of some geometric objects like unit disk graph or disk graphs. So these are my objects, and generally most NP-hard problems turns out to be slightly more easier. And I will explain to you what do I mean by slightly more easier. So what do I mean? So running time is still exponential, but it is not exponential in the truest sense, because look at 2 power big O of n algorithm for say 3 coloring. You can solve 3 coloring in planar graph in 2 to the power big O of square root of n. So it is still exponential, but it is much better than 2 to the power big of n. Say independent set. We can find independent set in a general graph in time n to the power big O of k. You try every k size set and check whether it is independent or not. And actually it is optimal. I mean, you cannot do better than this. This trivial algorithm is the best you can go for. But in planar graphs, you can do n to the power big O of root k. You can do even better. But for now, this is what I mean. And maybe for k-path or some problems for which in setting we have 2 to the power big O of k poly n, we might be able to get 2 to the power big O of square root k in 2 poly n algorithm. So this is what I mean that these problems become easier on these graph classes. Okay? So basically by easier I will mean better exponential time algorithm. Okay? So I will first tell you how to derive subexponential algorithm using treewidth. What is this notion of grid minors and bidimensionality, and how to go beyond bidimensionality. And if I have time, I'll talk about pattern coverage. At least I'll give you the statement of the pattern coverage, which is like, in my opinion, it's like a hash functions for graphs. Okay, so that's the whole idea of my talk. Okay, so what is treewidth? Treewidth is a measure of how tree-like the structure is, and I'll quantify what do I mean, how tree-like structure is in the next slide. But if you do not understand what tree-like this means, you have to go back to the book, read the chapter, and get a sense for yourself. Okay? So we will need 2 basic facts, which I'm not going to prove. One basic fact is that if G has a graph, if graph G has treewidth k, then many classical entry mark problems can be solved in time 2 to the power big O of k poly in n, or 2 to the power big O of k log k poly n, and which will be the case for all the problems we will consider. There are many problems, even on graphs of bounded treewidth, which does not have this form of running time. You can provably show that the running time dependence should be at least 2 power 2 power 2 power k. So there was an IQ paper which showed that the best we can hope for is triple exponential, otherwise things will go south. Okay? And another fact which I'm going to assume is the planar graph has treewidth order root n. Okay? And this was proved way back in 70s, and in fact the classical paper of Untitled used this notion of separated design many interesting algorithms on planar graphs already in 70s. I'll give you how you can design algorithms if you assume these 2 facts. So just a small slide on what treewidth is. So basically think of this way, that your graph essentially is what people say is like tree line. Okay? So given a graph G, which could be anything, I want to associate a tree G with certain properties. Now basically what is the property? So basically you have a function from vertex set of 2t to 2 to the power vertex set of g. So basically every node here will have an associated subset of vertices, right? 2 to the power vg, so it will have an associated subset of the vertices. And this is what is traditionally called path. Right? So the best way to think, how do I measure how tree-like my structure is? So hey, here is my tree, first of all. And for every vertex, every node in this tree, I have an associated subset of vertices. Now, I mean, what do I gain out of this? I mean, it cannot be any arbitrary association. So you request certain properties of vertices. So for example, what do I expect? I expect that if u and v are neighbor in my graph, it means they are adjacent, they have an edge between them, then there is just some bag here, or there is some node here, such that if you look at beta of that node, both vertices are present. So this is not any association, this map satisfies some property. So first property, let's call it edge property. So what is an edge property? For every edge, there exists a node, so that beta of that consists of sec u comma b. So this is what I mean by edge property. What else? It says that look at any vertex. Look at any vertex of your graph. Now this vertex can appear in many associations of beta, because I never say that beta has to be partition of vertex and nothing. All beta does, for every node in my tree, it associates a subset of vertex. Now basically he says that, oh, look at those vertices, fix a vertex, look at those nodes in the tree whose corresponding back has this vertex. You want them to be connected. Okay? So this is like connectivity property. Okay? So now in my example, let's look at my example. If you look at this graph, this is my tree decomposition. So basically what it means that this is my tree, and for this vertex I have associated which vertex? C, D, F. C, D, F. For this vertex I have associated B, C, F, and so on. Now look at any edge in my graph, C, D. Do you find a bag containing both C and D? Yes, there it is. Now let's pick an arbitrary edge, E, F. I'm sure there will be a bag containing S. Look at B here. Now let's fix up vertex B and look at all the nodes where B appears. B appears here, B appears here, B appears here. This is a subtree. Look at F. F appears here, appears here, appears here, appears here. This is a connected object. Right? So that is the property which we would like to maintain. Now, what is an idea? So the idea is that you look at this, if you look at this tree decomposition and look at a particular bag and look at the graph where this bag and everyone below, then the idea is that this subtree communicates with the outside world only via the root of the subtree. So the only vertex which can have edge outside the world, outside any vertex, must be the guys which are in the root. So for example, look at here, we have B, C, F. B, C, F. These are the only vertices which have an edges to an outside. In other sense, if you delete B, C, F from the graph, then look at any vertex which is in the below subtree cannot have an edge to any vertex which is on the top. So basically, another way of thinking is, if you look at a tree, you know that I can find a vertex in the tree which will balance my tree in completely balanced way. And what do I mean by this? There always exists a vertex in a tree. If you delete, look at any connected component, number of vertex it has is upper bounded by half of the original number of vertices, n minus 1 by 2. And this property is deleted. It means you look at any induced subgraph of the tree, this property holds. What is the property holds? That I will be able to find a vertex which if you delete, then look at the connected components there. No connected component will have size more than, or size is upper bounded by the half of the total size of the subject. Now tree is about one vertex separated. Why can't I have, yes, please? No, this is like just a subset. There is no ordering in there. Now, tree is an example where this property holds for one vertex. Now, there could be a graphs where this property will hold with 100 vertices. What do I mean by this? Then given a graph B, I can find 100 vertex. If I delete, every connected component has n minus 100 divided by 2 vertices. And this is not only true about the original graph. You give me any induced subgraph, I will be able to find this property that if you give me 100 vertex, I will find 100 vertex, delete it, every connected component of this induced subgraph has, suppose this induced subgraph had 5,000 vertices, so 5,000 minus 100 is 4,900 divided by 2, 2,450 vertices. Okay, I did my maths correctly. So what I mean, this property, what is this property? For any induced subgraph, if it has a size P, then I will be able to find a T-sized subset whose deletion will give me connected component of size at most P minus T divided by 2. it holds for subgraph also. Because, I mean, if it holds for reduced subgraph, it holds for subgraph. But it's better to just say for reduced subgraph. And by the way, this is all the treewidth is. This is all the treewidth is. These two notions are equivalent. You can prove it. If, like, of course, modulo some constant like 3 or 4, but if a graph has this property, then its treewidth is some block times this. If a graph has t, then this property holds, and you can prove. This is a very good exercise. Good exercise for graduate students at least. To prove that if a graph has treewidth t, then this property holds with t plus 1 size set. And this will hold not only for vertex set, it will also hold if you put weights on the vertices. Then you have to say, oh, weight gets divided. Now, why this is cool? Because if you have learned merge sort in your classical calculus, then what do you do in merge sort? Well, I do left, solve it. I do right, I solve it, and I merge. Now, I have found this small subset of vertices. After each deletion, I have different connected components. Now, if the problem which I am interested in does not have to worry about how I solve solution in one connected component and how do I solve problem in another connected component, then I can just go and solve problems separately on each connected component. Then this is not a multiplication of running time, it's an addition of running time. And then I would like to combine this, but they are like a small hub which is connecting to everybody. Maybe I don't have to solve independent set, but maybe I should be solving some slightly more general problem on this graph class so that I can combine. So this is where the treewidth is helpful. Now this is if you think in the divide and conquer way. But what does dynamic programming do? Dynamic programming is a way to arrange your computation in an efficient way so that you do not have to recompute several things again and again, right? And this is where this tree is very helpful, because what I try to do, I try to compute this tree decomposition and make a table of information which I need. If you have ever done, say, what you call some small dynamic programming over trees, if you notice that if you are in the middle of the computation for independent set, you have two variables: independent set containing this node and independent set not containing this node. This is the two information. Do you really care about what the tree is below? No, all you care about these two information, right? So if as an oracle, every node you come and ask me, and if I give you this information, it's good enough for you to get the final answer at the end. So basically, this object never even looks at it, right? So for many dynamic programming algorithms, if you have ever read Mahin-Nerod theorem in your stringology, then this is nothing but any algorithm on graph of bounded treewidth is nothing but doing some Mahin-Nerod computation basically on a stereoids. That's it. So if you're happy with x, y in the language, if and only if xz for all z in sigma star, xz in L, if and only if yz in the L, then this is what it is. Because this two-sized table, I'm going to give you many different trees who will have the same table. Then basically all I'm trying to tell you is that all those trees are identical in whatever setting it is, right? In their equivalent in some setting. So if you are familiar with language theory, this is what it is happening, right? So of course you have to go from a normal automata to tree automata and define everything. But besides those points, I mean, whichever way you would like to see, you can see, and if it is helpful to you, it is helpful to you. Okay, so much about tree decomposition. And and there are some very nice algorithms to compute tree decomposition. So given graph G and number W, you would like to know whether the tree width of this graph is at most W or it is strictly more than W. Then there is an algorithm in time 2 to the power big O of WQ dot N which can identify. By the way, trees has tree width 1. There is also a 4 approximate decomposition in time 2 to the power big O of W into N square, and this comes as a small lemma or 2 small lemma in the classical paper of Robertson and Samuel where they define tree decomposition. And later people got a linear time file approximation in 2013, and also a classical polynomial time approximation algorithm, which does order square root log w in polynomial time using very nice methods of STP and all those things. So you can do all nice tricks and techniques which you learned in approximation algorithm, throw on this problem, and you can find vertex balance separator using all these tools. Okay. So since the kind of application he will be interested in, 2 power big O, we assume that 2 to the power, we will compute our tree decomposition in time 2 to the power big O of w, and it will be some constant factor approximation. Okay. So as I promised to you that I will not do vertex plot, let me tell you how you do DP on graphs of bounded tree width, say for 3. So you are interested in whether the input graph is 3 colorable. Okay, so I will give you an algorithm which will compute 3 coloring in time what? 3 to the power w times w to the power big O of 1. By the way, this algorithm might look very trivial, but this is the best algorithm. So what I mean by this, you can show unless SAT has 2 minus epsilon to the power n algorithm, unless SAT has 2 minus epsilon to the power n algorithm for some epsilon, for any epsilon equal to 0, 3 coloring on graphs of bounded tree width or graphs of tree width w cannot be solved in time 3 minus epsilon to the power tree width into any power of 1. So this algorithm, which is very simple, which I will tell you in a minute, is actually optimal. So if you do this better, you will get them. Yes?
SAT or
SAT. It's not 3 SAT. That is why I know 2 minus epsilon n. If it is 3 SAT, will come back. You will see in a few minutes that's like a exponential time hypothesis. So I did not give you the name, but this is basically what is called strong exponential time hypothesis in this. So think about this. I mean, what is P versus NP? I mean, you prove lots of things versus P versus NP. Basically, all you are doing, P versus NP is not a theorem. It's a conjecture, which basically says all these problems cannot have polynomial time algorithm. Now, if that conjecture is valid, you prove certain kind of things. Similarly, people in exponential algorithm make similar assumptions about satisfiability of SAT, right? So P versus NP is SAT cannot have polynomial time algorithm, but SAT may not have certain other kinds of algorithm, and that has a different consequences. So, for example, if I assume that normal SAT with no restrictions on variables or this, look, if it has n variables, you always have to put n poly n plus m algorithm, because you try all assignments and test. But what it does that our best efforts over the last 35 years or whenever the computer science has come, we do not know an algorithm is running like 1.999 and as many lines you wish to put to the power n. Okay. So how does my 3 coloring algorithm works? Okay. So my 3 coloring algorithm works as follows. I said, look, I don't know how the 3 coloring for the below graph will look like. I have no idea. But when I restrict my 3 coloring to this small bag, it will have any 3 coloring of this vertex. So how many possibilities are there of 3 coloring of say t plus 1 vertex? 3 to the power t plus 1, right? It could get red, blue, green. Second vertex can get red, blue, green. So there are t plus 1 vertices, so 3 to the power t plus 1. So these are my partial solutions. This is what I mean by partial solution. And Vx is all the vertices here. So basically you think of restriction to this. And now I make a Boolean variable for every node x and coloring Bx to 1, 2, 3. We compute the Boolean value Exe, which is true if and only if C can be extended to proper 3 coloring below. So if you get 1, if I say, if these three guys, if this bag is, if I fix the coloring of this, is it a way to extend this coloring to the graph induced on all the vertices below, which is consistent with this? If it is this, then I put 1, otherwise I put 0. So basically I have a table of size 3 to the power treewidth, and some 0, 1 in the last column, which tells us whether this is extendable below or not. Now, actually, what you can show that you can determine this Boolean value by looking at its children. You don't have to go below. Okay? And this is a very classic standard classroom exercise, so I will not teach it. But this is what you do. What is the main idea? Look at the problem, look at the optimum solution, look at its intersection with this bag and everything below, right? That is your family of partial solutions. What is our family of partial solutions? Everything which intersection is below. Now, what are you trying to do? You are trying to come up with an equivalence relation on this partial solutions, which will tell you that, oh, these solutions are same for me, because if you gave me any of them, I can extend it to the whole thing. And basically, your table size is the number of equivalence classes, this equivalence relations. That's it. Okay. So much about decomposition, so much about treewidth.
So, Saket,
yes?
For each step, subgrid and right subgrid problem, you get a consistency.
Yes.
You have to, so then it is not
Because you're right. If you do that way, yes. But we can assume that this tree can be structured much more nicely. In what sense? Whenever I have a join node, then both nodes have the same vertex set. So if I'm looking for a consistency for this, then I say, hey, if this is, I just look at exactly the one particular coloring here, which is because the bag contains the same vertex. Think of this way. I have a set here. I have decided which coloring I'm going to take. So then you should be consistent with the same coloring in the left graph. You have to be consistent with the same coloring in the right graph. So if I make a node, whenever I have a joint node with two children, it's the same vertex at both. So in some sense, I have made a copy of it, and I say, okay, look at this guy here. Is it consistent here? Look at this guy here. Is it consistent here? I am consistent if and only if this is consistent and this is consistent. So now, if you index your table properly, then you just have a two table copy. Okay? So you can do these kind of things. Okay. So please feel free to ask questions. I'm not in a hurry. I mean, I'll go along. These slides are just suggestive. They are not, I don't have to complete them. Okay. So now I told you how to do tree coloring in 2 to the power big of W poly n on graphs of tree with W. Now we know from the Robertson scenario that planar graph n vertices has tree with order root n. So did we make an algorithm for planar graph which runs in time 3 to the power big of root n? Let's just combine, right? Textbook algorithm plus combinatorially bound implies a subexponential algorithm, right? So I have a planar graph. What is this tree with? Order root n. I have an algorithm which can do in 3 to the power w. So put this big of root n on w, and you have 3 to the power big of root n algorithm for tree coloring planar graph. So this is how you design classically subexponential algorithm. So this is not, it's a Lipton chart in 17s. So I have started from 17, so this is like Lipton chart. Okay, world has gone way beyond. I hopefully I will be able to show some glimpse of the world 2016. Okay. Yes. Yes. They'll get there. I'll get there. Okay. So what did we learn? Textbook algorithm plus combinatorial bound implies subexponential algorithm. Look at Tarzan. He didn't know all this tree with business. People didn't even define this for him. Poor Baker. People didn't even define tree widths. He had to do all this DP all by her hand and define whatever treeness meant all by hand, and it was so difficult for her. But now technology has improved so much more. Okay, so now what I would like to tell you, so two natural questions. Can we achieve this running time on Jagger graph? And can achieve even better running time on planar graph? So what did I give you? For tree coloring, I gave you an algorithm which runs the time 2 to the power big of root n on planar graphs. Okay. Is this phenomena also happens on general graphs? Or can we do even better on the planar graphs? Let's look at the answer. So as I told you before, P naught equal to NP is not sufficient for sufficiently strong hypothesis to rule out these algorithms. Okay? So we need a stronger hypothesis. And I didn't come up with a stronger hypothesis, someone did. And this is a hypothesis by Impagliazzo, Paturi, and Zen. What do they say? And whatever they say, they do not say exactly this, but you can derive from their statement this statement, that there is no 2 to the power lit of n time algorithm for n variable 3 SAT. So now we are talking about not general SAT, but SAT where every clause has size 3 and n is the number of variables. Okay? So what is this statement tells us? That let's assume for now that 3 SAT cannot be solved in time 2 to the power lit of n time. And the current algorithm for 3 SAT is 1.30704 to the power n by R3. But let's note one thing. N variable 3 SAT can have how many clauses? N number of clauses could be as bad as n cubed. So let's ask ourselves the following question. Are there algorithms that are sub-exponential in the size n plus n of the 3 SAT formula? Right? Yes, you said that the 3 SAT cannot be solved in time 2 to the power little of n, where n is number of variables. Okay, I assume this as my hypothesis even then. But can I get an algorithm with running time 2 to the power little of n plus m, where n is number of variables? Why? Because notice why it is interesting. Look, 3 SAT can be solved that much faster, but it can also be solved in time 2 to the power n. Right? There is an algorithm which runs in time 2 to the power n. So if n is say at least n square variable, then how much this algorithm runs? What is the running time of this algorithm in terms of n plus n? This is nothing but 2 to the power big of square root of n plus n. Am I right? So if I take n plus m as my measure of running time, then the 2 power n is 2 to the power big of square root n plus m if my m is n square. But if I assume that the m is like n square, if I assume that m is like omega n cube, I get even better. Really? So, but if I do not assume anything about this, I want a non-uniform algorithm which given an n variable SAT, with 3 SAT with n variables and m clauses, gives me an algorithm of running time 2 to the power say square root of n plus n always. Is it possible? We know that this is possible when m is like n square, when m is like n cube. In fact, this is possible if I just say little of n plus n, then this is okay for any graph which where omega n some n to the power 1 plus epsilon. Like for any epsilon greater than 0, you can prove that you will get such a number. So like if the number of consecutive number of edges is slightly larger than linear, you start getting some. So what is this big deal about all this? Well, there is a big deal about all this, and there's a famous lemma which shows by there's something called sparsification, which basically tells you that look, in sub-exponential time, I can come up with sub-exponentially many instances of 3 SAT. How many instances? Sub-exponentially many instances of 3 SAT, where number of variables and number of clauses are actually same, like order. Of course, I'm hiding the right details, right constants and everything, but essentially it means that in sub-exponential amount of time, I can come up with sub-exponential instances. For our purposes, let's say one instance where the number of variables and number of clauses are like n variables and n clauses. You just now assume that I can prove the power little of n algorithm. So now this instance, if I can have 2 to the power little of an algorithm, then I have 2 to the power little of an algorithm for 3 SAT. It contradicts my assumption or conjecture, whatever you want to say, right? So we do not expect to have even an algorithm of form 2 to the power little of n plus m or n variable m clause 3 SAT. And this is great news. And this is something which is very technical and it requires at least 2 lectures to teach, so I will teach anything. But again, if you want to know more how this lower bound tricks are applied, look at the lower bound section of the book. It will have all those. Okay, so what did we learn because of this? Okay, so if you look at the textbook reduction from 3 SAT to 3 coloring in the graph, in the book, textbook reduction. What it does, n variable m clauses, it reduces to graph G on order n plus m vertices and order n plus m edges. Now I can start with 3 SAT basically with m being order n clauses because that is where the instances are hard actually. So what does that imply? We can assume that order m vertices is order m edges and n is like order m. So assuming ETS, there is no 2 to the power little of n algorithm 3 coming on an n vertex graph G. So this 3 coloring phenomena which we saw 2 to the power big of root n on planar graph, we made an algorithm. We cannot hope to make such an algorithm in graph. We cannot even hope to make an algorithm 2 to the power big of n divided by some function of n, fn, where fn is some monotonically increasing function. However slow, log star. You cannot hope to make such an algorithm. This is what this statement tells us. Right? So this great news which we had about planar graph, it is there at planar graphs. And you can, assuming ETH, you can transfer all these lower bounds to polynomial and all these bounds because if you look at the textbook reduction, it takes n variable SAT with m clauses to order n plus m vertices, n plus m edges. So all this classroom textbook exercises will give you cannot have assuming ETH to the power little of for independent set, click, dominating set, vertex curve, feedback vertex, any bound. But not always. Okay? Okay. Now let's make lower bound based on ETH. So we had another question. Okay, we made 2 to the power big of root n algorithm for 3 coloring on planar graph. Is it possible to get m to the power 1/3 in the exponent? Let's try to roll out that. Okay. How? The textbook reduction from 3 coloring to planar 3 coloring uses, if you know your textbook, NP hardness and reduction, look, I'm not using more. Then basically you will encounter this crossing. So what property of this crossing? So basically, in every 3 coloring of the gadget, opposite external connectors, these are like 4 connectors, have the same colors. So if this gets green, this should get green, this should red, then this should get red. And you can prove that if the opposite connectors get the same color, then you can always extend inside to a 3 color. And you could have, but I'm not saying that if the 2 guys have to be green, the other guy have to be blue. All the 4 connectors could have the same color. But all I'm demanding is that if I am getting green, then my diagonally opposite guy should also get green. I'm not saying that this guy should get a different green and this guy should get red. No. All I'm demanding is that me and my opposite guy have the same color, then you can all extend this. Now, how the reduction works? Basically, in the planar graphs, basically you start with general graph. You start with an embedding. They might cross. What is the cross? And this is like 4 jumps. You delete this part, and from the 4th connector, you add your gadget. This is exactly how you make your reduction for planar graphs. Yes, Neil, you look very suspicious. No, this is edges, like 2 edges cross. So think of this 2 edges cross, 1, 2, 3, 4. four new points and delete this internal and put this caret. Now every crossing you have represented this way. Yeah, you can just make it. Yeah. Yes. Yes. What? Look at planar graph. Okay? Draw them on the plane. Like non-general graph. Draw them on the plane. And two edges will cross, right? Non-planar graph. Each time they will cross, I will replace this crossing with this caret. Each time. Let's see how much is the blow. So each crossing you have order one new edges or vertices, like basically some 10, 12 vertices here. So a graph with n edges can be drawn with order m square crossing. Why? Because look at, there are n, everyone can cross. You can actually prove, I mean it's not trivial, but you can show that everybody can cross and they do not need to cross more than some constant number of times. So there is an order m square crossings. And for each crossing I will place this. Now what did I get there? Well, I got 3 stat formula, n variables in project, graph G, order m vertices, order m edges, implies planar graph G implies order m square vertices, order m square edges. So assuming ETH, I cannot have 2 to the power little of root n. Because why? If you have 2 to the power little of root n algorithm, then I take this reduction, pi times this, give me my algorithm. That guy gives me an algorithm and I can just transfer back. So what did we learn? So this 2 to the power big of root n algorithm which we made for 3 cutting is actually optimal under ETH and it was already observed by Kai and Zuras in 2001. So we have reached 2000. Okay? All good? If you have questions, please ask because this is the first thinking point before I'll forget you and say goodbye. Time factor approximation, so that doesn't cost too much. Or you can apply this 3 to the power factor 4 approximation of 2 to the power big of W. W is root n, so that's fine. Right, but best thing is to do polynomial type factor 4 approximation. Yes, but for planar graph you do factor 4 approximation. In fact, it would be better 3 by 2 approximation. Okay. So this is my summary of my chapter 1. I spent a lot of time. Upper bound, standard bound treewidth algorithm plus bounds of planar graphs gives you an algorithm. Lower bound, textbook NP hardness proof with quadratic blow up plus ETH rules out 2 to the power little of root n algorithm and it works for all these bunch of problems. Okay? Fine. Okay. This is my end of my word chapter. Let me move to the slightly more complicated algorithms. I have time till 11:35. 10 minutes. Okay? So don't worry. This is what I told you that I'll teach you something nice and then we forget it. Just go ahead. Okay? I will not do chapter 3 for you, but I'll tell you what the last step on this word is. Okay. So what does big minor and bidimensionality mean? Is basically what is FPT is like more refined analysis with n and k, and we would like to compute an algorithm with running time f of p poly n. And what we know for the first 2 problems, we have 2 to the power big of k poly n algorithm, which is best possible on general graphs. Okay, and for negative wavelengths, we should have the hardness. So now, what kind of upper and lower bounds we have for this? For most problems, we cannot expect a 2 to the power little of k poly n algorithm. Why? Because that will imply 2 to the power little of n algorithm, and that we have already ruled out. Similarly, 2 to the power little of root k algorithm doesn't make much sense because we have already ruled out 2 to the power little of root n algorithm, and in most of the settings we want k is less than equal to n. So this is what you cannot expect such a number. But what about minimal algorithm, right? So we will show that on planar graphs there is a general methodology which gives you 2 to the power big of root k algorithm for a variety of problems. And let me do this sub-exponential for k-path. My topics first thing, and then in 2 minutes I'll get to the last one. Okay. So there is a notion of minors. What is a minor? Is basically H is called a minor if you can get this H from G by the following operation. You are allowed to delete a vertex, you are allowed to delete an edge, and you are allowed to contract an edge. So for example, if I contract UV, I get this. Meaning you identify your V, delete the self loop, and delete the pattern. Some definitions allows parallel edges, some definitions allows self loops. Depending on the applicability, you choose whatever you feel like. Okay? So this is what. Now notice, if the original graph had a path of length k, and I do these operations, can I increase the length of the path? If I delete an edge in the graph, can I increase the length of the path? No. If I contract a vertex, I can never increase the length of the path. Right? I can reduce. I'm not saying that you cannot make it smaller, but you cannot increase it. That's all that is. Right? So let's quantify this. And what does it mean? So there's something called planar excluded grid theorem. Now people ask, what makes the treewidth of graph large? And people found a most canonical example to be the grid. You can show that a k cross k grid has treewidth k, exactly k. And what Robertson said in 1994 along with Thomas, that every planar graph which has a treewidth at least 5k contains k cross k grid as a minor. And from 90s, we had this big conjunction that this should hold also for general graphs. The bound we knew that if the treewidth is more than some 2 to the power poly k in 90s or till 2012, if the treewidth is more than 2 to the power poly k in general graphs, then you have a k plus k grid as a minor. And the lower bound was very rare, k log k. You could never prove anything more. And in 2012 or 13, both Chakuri and Julai, not graph theorists, showed it is enough that if treewidth is more than k power 100, then you can get k plus k grid as a minor. And in, I think, Stock 2016, she improved this number to even smaller, k power 90. So, but still, lower bound is k log k. So, or you can, so there's still far away from k log k to k power 90. It's still long way to go. Or even to improve the lower bound. Okay, so that's the hard part. So here is an algorithm for k-path. How's an algorithm for k-path? See, if the treewidth of a planar graph is at least 5 root k, it implies that it has root k cross root k as a grid. Let's take this grid minor. What is the size of this? Root k cross root k. How many vertex a root k times root k grid has? Do we know how to multiply AB? It's k, right? And here is the path. Look left, take like this, take like this, take like this, take like this, take like this. Hit the path. So you can actually show that if the treewidth is very large, then have a big grid. If I have a big grid, then have a big path, which you can prove. I can extend this path and get a path in my original graph. So if the treewidth is large, then I'm done. Right? And this is what it tells. The grid has path of length at least k, which implies you get a path of length at least k. Prove for yourself that even when you did this operation, there is a way, and if you found a grid as a minor and found a path, you can get a path in the original graph by doing the reverse tweaking. Prove it for yourself. Okay? So what is our algorithm? Well, we use the observation to find a path of length at least k on planar graphs. Treewidth is larger than 5 root k. Answer is, there is a path of length at least k. If the treewidth of W is less than 5 root k, then what do you know? I know my algorithm from my 2 to the power big O of W algorithm, right? So I substitute 2 to the power big O of W algorithm with big O of root k, and done. So happy. Right? So this is a very clean and nice observation. I think Ibn, Hajagai, Tilkos, and Bhumi wrote a JSM paper in 2005 using these ideas. So basically, algorithmically, you find an order 1 approximate decomposition, and then you answer everything appropriately. Okay, so let me give you one definition that will help you get some flow. So a graph invariant, like k-path, is a graph invariant, is called minor bidimensional. Why bidimensional? Because of its value on the grid. If I take any minor of this, the value of this does not increase, like k-path. I took any minor of this, its solution remains at most, it doesn't increase it. For example, look at a planar graph and look at a problem called dominating set. If I delete an edge, dominating set can increase. Because before that edge was dominating, but if I delete this edge or delete a particular vertex, dominating set size will just blow up. So dominating set is not minor closed object, but some people are. And for those people, we can give a very nice algorithms. Okay? So, for example, look at minimum vertex cover. And what else? On this tree grid, on the grid, your solution on k cross k grid, your solution should have size some constant time k square. For example, look at minimum vertex cover. Of course, look, it's like it has some k square by 4 or 2 matching. If you have much of matching, any vertex cover must pick one vertex from each of this, so you have this property. Longest path, you just show. Feedback vertex, make a small 50 cycles of 4 lengths each, and then you have. Right? And these are minor bidimensional. So this is what I mean by minor bidimensional. Right? The solution does not increase under taking minors, and on the grid, its size is at least c times. And so this is my end of the chapter. Basically, this is what we do with bidimensionality. Is that standard boundary field algorithm, planar excluded grid theorem gives you an algorithm, and very trivial NP hardness proof with quadratic blow up gives you a lower bound, independent set, dominating set. Also can be put into this framework, but you do not allow the deletion operation. Only thing which you allow is contraction operation, because then you can prove that dominating set size will not increase. Okay. Okay. So okay. So what are the limits of bidimensional? Let me tell you this, and then I will flash you one slide. Done. So you are given two graphs H and G, and if you have to decide if G has a subgraph isomorphic to H. And what does subgraph isomorphism of planar graphs tells us? That Epstein proved in 1999 that you can do in 2 to the power big of k log k times n, where k is a pattern graph. So if you are looking for planar graph, it is clear that H is also plane. Otherwise, what is the meaning of planar subgraph isomorphism? Now the question is, we were talking about this one square root all the time. Does this also happens for subgraph isomorphism on planar graphs? And recently, in ICAR 2016, Bodlander, Rizaloff, and Wendell can show that you cannot have an algorithm with running time 2 to the power little of k divided by log. So at least this is cool. You cannot have. It's a very cool reduction, simple, but it's nice reduction. But there is a randomized algorithm which actually achieves this. So it's quite curious kind of lower bound and upper bound. You cannot have little of k divided by log k. Okay? So, and for all these kind of problems like subgraph isomorphism, I don't know how to apply this bidimensionality. In fact, there are some counting versions you can show this trick of bidimensionality doesn't work. Okay, I'll just go, and go. This is my book. Let me go. Okay. So, what are the items? Now I have reached the end, don't worry. I am not going to prove. Large grid minor implies certain answer. It's very strong. In what sense? Whatever directed k-path. Now, simple path of k vertices in a directed graph. Now, If now, first of all, what is the tree width of a directed graph? No one understands it, or they are still, as a community, are trying to understand it, and still it is not useful. Just forget it. So whenever I talk about tree width, I mean tree width, and you forget the direction. So even if I have a big grid, what does it mean? When I look back in my graph, I mean direction will be all over the place. So even though in the underlying graph I have a long path, but when I look at the direction of arcs, edges, makes no sense. Looking for directed k-path. Okay. So, okay, fine. If I want to find k-paths of maximum weight, yeah, if I have a grid, all I was able to conclude, if I have a large grid, it has a path of length at least k. But it may not tell me anything about length of maximum weight path. Or what about cycle of length exactly k? No, it doesn't give me any information. Now the question was, when I say tilde, I'm hiding some polynomial here. Can you solve to the power big O of tilde root k poly n on planar graphs? Until recently, and by recently I mean until a few months back, with no algorithm. But now, so in general we can ask the following question. Let a k pattern be a vertex subset of P such that size of P is less than k and graph induced at P is connected. So think of a path as a pattern of length k and it is connected. And we are looking with k patterns with this kind of property. So what is our idea? Our idea was to find a small family of subgraphs that covers all patterns, and this subgraphs has small tree width. Which I would wanted to just show you. So suppose G is a planar graph on n vertices, and suppose k is a positive integer. Then there exists a family f of subset of Vg such that. So I'm going to give you so you give me a graph G and a number k. I'm going to output your family of induced subgraphs of my graph. And what is the property first? Size is not big. Size is like subexponential, 2 to the power big O of root k poly. But it is like a hash function. In what sense? You give me for each AF, first of all, the tree width is small. Not only the size of the family is small, the graphs which I have given you, its tree width. And the third property is for every k pattern P, there is some AF such that P is contained inside K. What it says? Look. You give me a number k and g, I'm going to output a family of induced subgraph of my graph. Family is subexponential, and each object in this has small tree width. And what is the property? Why this I call pattern covering? Now, for any subgraph you give me, there is some object which is in some subgraph where this guy is completely contained inside this. So now apply, and this can be completely randomized. Done. So how do I apply for directed k-path? I said great, construct f. For each AF, try to find a k-path in graph induced at A and B. That's it. That's the number. No. I suggest planar graph. There's nothing to do with undirected, directed, nothing. It's tree width is up underlying undirected. So it's a planar graph. My family, every object, when you forget the direction, has a small tree width, but you can have anything. Now you give me your k path, you give me your k tree, you give me your any pattern, there is some guy which contains it. So this is exactly like a hash function. For each AF, try to find k path in graph induced to A by dB. Okay? And this applies to directed k path of largest weight, cycle of length typically k local search, of course this nice good algorithm on graph of boundary decomposition, subgraph isomorphism. You can just tweak their local bound to get graph bound. So not a big deal. Okay. And this is where I'll give you I'll not give an example, but how do you do this? If I give you a k grid, how do you get such a family? That's a good homework exercise. Okay? Everybody was talking about Baker. So please do Baker. Right? I gave you a k cross k grid. And I want to find the hints, please think of paying. She will help you. Okay? And statement is randomized and we do some tricks. Okay. So basically, what is the conclusion? That we still need some robust understanding of what you can do into the power big of can or cannot do, and for some specific problem, you have to go beyond the known toolkit and eventually invent completely new tools. So this is a great thing. And for example, one problem we still not able to do anything is something called standard tree parameterized by number of terminals. So in general graph, it is 2 to the power number of terminals, but in planar graphs, we don't know what the status is, as far as I know. Last, so I taught you a little bit about how to derive sub-exponential algorithms using treewidth, how to use grid minors and bidimensionality. I did not teach you how to found bounded treewidth solution, and I told you at least what is pattern coverage lemma is without telling any proof. If you can make use of that for your algorithms, please go ahead and make use of it. And much more to be explored here, because this is a randomized algorithm. We don't know whether we can do deterministic, whether the polylog factor is right, whether we can extend it to H minor free graphs, blah blah blah. We have no idea. It's just a tool. And thanks for listening.